Hello everyone, welcome to this webinar on concentration-QTc modeling with the MonolixSuite. My name is Géraldine Herald and I'm the VP application at Lixoft. It is my pleasure to introduce Monika Twarogowska, which will be our speaker today. Monika will show you step by step how to perform a concentration-QTc analysis with Monolix. I now give the mic over to Monika.
Thank you, Géraldine. And welcome everyone for this webinar, and thank you for registering. I will start the video so you can see me during the talk. So probably everyone has seen the ECG recording. Here on the left, we have normal heart rhythm, where the ventricular polarization and depolarization is regular, and also the time when the cardiac ventricles start to contract and when they finish relaxing is regular. This time is called a QT interval and is used to assess many heart rate properties. When this QT interval becomes too short or too long, it causes a situation when the polarization and depolarization becomes uncoordinated, and it leads to irregular heart rate, so the so-called cardiac arrhythmia. An example of cardiac arrhythmia is torsade de pointe, which literally means twisting around the point. The QT prolongation can be inherited in different syndromes, but also can be acquired during, for example, treatment with certain drugs. In fact, in the 90s and early 20s, several drugs have been withdrawn from the market because they were correlated with the sudden cardiac death. However, there are situations in which benefits of taking a drug is much higher than the risk involved with the drug-induced QT prolongation. And this is why currently all new drugs are required to undergo an assessment study that tests a potential risk of drug on the prolongation of the QT effect. And this risk assessment, in particular using concentration QT analysis, is the topic of today's webinar. So I will first give you some motivations, an introduction, why concentration QT studies are used for this risk assessment, and what are the modeling recommendations, so guidelines for this type of analysis. And then in the second part, I will present you step by step how to implement these modeling recommendations in Monolix. So let's start with the first part. Actually, the first question is what we should measure. So what we should measure to assess objectively if the QT interval length was prolongated or not. We know that QT depends on heart rate, so to compare it, to compare its measurements at different times, we have to correct it to make it independent of RR interval, and there are multiple formulas for this kind of normalization, and the most common method used for healthy subjects is the Friederichia formula, which is presented here on the right. After this correction, due to the dependence on heart rate, we adjust the QTc to baseline. So we calculate the so-called delta QTc. And there are two typical methods to collect the baseline measurements. One that is recommended for parallel studies, for parallel design, is a time-matched baseline. So the measurements taken during 1 day before the treatment at fixed time, so at predefined time points that are going to be used also during the treatment. In case of crossover design, it is sufficient to use a pre-dose average baseline where we have, for example, a triplicate of measurements just before the first dose. But actually, what we are interested in is not only change of QTc from baseline, but also the change adjusted by placebo. So the difference of this change from baseline between the drug arm and placebo arm. And in fact, this variable, so the so-called double delta QTc, is used in the decision criteria, so it's used to calculate the endpoint. In c-QTc studies, the aim is to analyze the largest mean effect, so the double delta QTc max, at each time point, at each measurement time points during the treatment. From the International Council of Harmonization guidelines, the study is negative, so there is a low risk of a drug to induce prolongation of QT if the two-sided 90% confidence interval of this double delta QTc max exclude 10 milliseconds at all time points. It means that the studying all time points means that the sample size can be very large, and because this is a dedicated study, the cost can be really high. In 2015, the FDA approved to use concentration-QT studies as an alternative analysis of drug-induced QTc prolongation. And in these studies, instead of analyzing time by time values of delta QTc, we analyzed at different concentrations which are of interest. So at therapeutic doses and supratherapeutic doses. And here, the decision criteria is that study is negative if the upper bound of the 90% two-sided confidence interval of this double delta QTc is less than 10 milliseconds at the highest relevant exposure. This study uses modeling. As a result, the measurements at all time points are used simultaneously. So we have more data. Moreover, we can, it is not a dedicated study, so it can be used already in the phase 1. And what is another advantage over c-QT study is that this approach can give us new insights. So we can use the model predictions to study, for example, new treatments or new administration routes. However, it is based on models, so it requires model assumptions, and different model assumptions can lead to different results. Moreover, the models can become very advanced, especially if you have complex drugs or drug combinations or metabolites that can lead to some delay between the exposure and response. So when using modeling approaches as a support for regulatory submissions, it is important that the methods are described very clearly and the results can be reproduced. Actually, this International Council of Harmonization E14 report doesn't give technical details what are the requirements for the modeling of c-QT studies, but the scientific white paper on concentration-QT modeling published in 2017 by Christine Garnett and colleagues propose certain recommendations on how to design studies that use c-QT analysis as a primary analysis for risk assessment. They also describe how to perform this analysis, how to build models, and how to report the results. So now I would like to describe briefly the the modeling part of these guidelines, because the guidelines for designing studies is kind of a topic for a different separate webinar. So I will present you the so-called pre-specified model for both delta QTc and double delta QTc, and the assumptions that are used to define these models, and how to compute decision rules. The predefined model from the white paper is based on the following assumptions. First of all, they are called exploratory plots because they can be assessed with specific graphical plots. And first, we have to check if there is no effect of drug on the heart rate, and if the correction of QT interval is independent of the heart rate. Then we have to analyze or explore the relationship between the exposure and the response. So if the relation is direct, which is the hypothesis for the predefined model in the white paper, and if this relationship is linear. The default dependent variable is this change of QTc from the baseline, delta QTc, and the model contains fixed effects here in blue and random effects. Here we have θ0, which is a fixed effect in the absence of treatment. Then we have θ1, which is connected with the effect of treatment, θ2, which is connected with the presence of drug, so with the concentration. θ3 is connected with time, which is associated with the circadian rhythm, that is with the daily changes of heart rate. And we have an effect of baseline. Random effects are added to two parameters, so to the θ0 and θ2. Additionally, the baseline is centered at the population value, that is the average over all measurements. From this equation, we can derive the equation for placebo adjusted delta QTc. So starting from the main equation, we know that the double delta QTc is the difference between delta QTc calculated for drug arm and for placebo arm. Treatment is a categorical covariate, so if we have drug, then it's equal to 1. In case of placebo, it's equal to 0. So now, writing this equation in these two cases, so for drug we have all terms, and in case of placebo, two terms disappear, so the one that is connected with the treatment and the one connected with the concentration. And now, subtracting these two equations, we obtain the equation for double delta QTc. And it contains three terms. So we have one term that is fixed effect associated with treatment. Then we have a term associated with the effect of a baseline, which is adjusted by placebo, and effect of the presence of the drug, so with the concentration. This model is a variation and is used in crossover studies when we can calculate for each individual double delta QTc at each time point. Now these two models can be used to calculate the endpoint. So if we have model-derived delta QTc, then the double delta QTc is a difference of averaged values of delta QTc. Average, I mean they are average over all individuals, one that is calculated at concentration of interest C and one at concentration 0. If double delta QTc is derived from the model, then the equation for double delta QTc is much simpler, and we can use directly here the parameters which are estimated during model fit, and the estimation should be done with maximum likelihood type methods. So now from this equation, the white paper gives also formulas for estimated standard error and for confidence, 90% confidence interval. However, this formula for the confidence interval is valid only in case of linear models. And even in this case, the number of degrees of freedom in the t-distribution is not clearly precise. There is alternative, which is just a simulation of model prediction and then calculation in the confidence interval using these results. So to sum up, the white paper helps to standardize concentration-QTc study. On one hand, it gives guidelines for the modeling of c-QTc and how to design the study to use this analysis. So it gives guidelines on the model definition, on the exploration of the model assumptions, and how to perform the diagnosis. On the other hand, it unifies the reporting. So it unifies what is needed for support of the regulatory submission. And the main goal is to increase how easy it is to submit them. And at LixOft, this is always our goal. That's why we are working on a package that can automatically perform all elements recommended by the white paper. And in short, you give a data set with your measurements from ECG recordings and concentrations, and you receive a report with results. And these results contain exploratory plots recommended by the white paper with estimation of parameters for linear and also for Emax models. The report contains also the diagnostic plots and with the results and calculations of the endpoints and double delta QTc at specified concentration. So it seems like kind of a black box, and this is why in the remaining part of the webinar, I will present you all the steps that are performed in this R package, and in particular, how the concentration QT modeling is implemented in Monolix. So at first, I will show you all the exploratory plots that can be generated. Then for the double delta QTc, I will show you step by step all the modeling workflow. And then in case of delta QTc, I will show you how to implement this model in Monolix. And finally, going a little bit further, I will show you how to use full PK double delta QTc model in Monolix. For this, I'm going to use an example of Dofetilide, which is anti-arrhythmic agent. So we know that it causes prolongation of QT interval. The data set is taken from a crossover study in which there is a placebo arm and a drug, during which individuals received a single oral dose of 500 micrograms of Dofetilide. The measurements were taken during 24 hours at 16 predefined time points. The first time point is just before the first dose, and it is used to obtain a pre-dose baseline. Measurements of concentrations of Dofetilide and ECG recordings are time matched, and from the ECG recording, there were collected 3 replicates for QT and for heart rate. Let's look first at the exploratory plots. These plots are generated with the R package that I mentioned to you before. And first, what we check is if the drug has no effect on heart rate. So this plot on the right is a time course of the change of the heart rate from baseline. And we see that in the drug arm and in the placebo arm, there is no big difference, so they are consistent. So we can assume that the drug has no significant effect on the heart rate. Then on the left side, we have a plot of QTc versus RR interval. In this case study, we are using the correction with the Fredericia formula. The regression lines are horizontal, so there is no relationship between QTc and RR. Next, what we assess is the relationship between the exposure and the response. So first, we have plots here for the time course of delta QTc and concentration. We can observe that the maximum of both is at similar time points. However, if you look at the hysteresis here, so the plot of double delta QTc versus concentration, we see that it is not clear if there is a delay between the exposure and the response or not. And actually, I will assess this problem in the last part, so in the PK-QT model. In the last plot of delta QTc versus concentration, we can see that the assumption of linearity is very likely to be sufficient, and also the effect of the concentration is homogeneous as points are symmetrically distributed along the linear line. In this part now I will present you how to implement this model in Monolix. So first let me start with opening the data set. One of the functions of the R package is that it takes your original data set, so almost raw data set, and prepares it for different parts of the analysis. So let me browse the data set. So what I mean that the data set is prepared for the analysis. First, in the observation, we have directly double delta QTc values, and they are averaged over 3 replicates that are from the ECG recording. The concentration is placed in the additional column, and we have also calculation of the baseline centered at the population mean and adjusted by placebo. So here, most of the columns are already tagged. I just need to select the centered baseline as continuous cover rate, and I can accept the dataset. So here in the plot section, we can see the double delta QTc spaghetti plot, and what we can verify is the effect of baseline. So in the stratification, I can select the baseline and color it, so we can see that some of the variability between individuals can be explained with this covariate. Okay, I will now save this project. Okay, and export it directly to Monolix. Okay, because all the applications in MonolixSuite, they are interconnected, so all the information about the dataset were automatically exported here, and I can just click next. But now, before choosing a structural model, let me explain you in detail how to implement the pre-specified model from the white paper in the Monolix. Okay, so this is the equation for the model defined in the white paper, where we have one term that is fixed effect due to the treatment, we have effect due to the concentration of the drug, and we have effect of the baseline. So we see that in the dataset, this effect of the baseline is tagged as continuous covariate, and concentration is tagged as regressor. Now, to implement this model in Monolix, the structural model uses only two parameters. So we have one parameter called intercept, which contains θ1 plus the effect of the baseline, and the second parameter is slope, which is the term that is multiplied by the concentration. So these two, intercept and slope, they are individual parameters. So now we have to define them, which means that we have to define the statistical model for them. And intercept is defined as a normal distribution around the population value. So the intercept pop here, which corresponds to the parameter θ1, plus the effect of the covariate baseline, centered baseline, with the beta parameter in Monolix that corresponds to the θ4 parameter here in the original model. There are no random effects, as you can see here, so this also has to be taken into account in the statistical model, which in Monolix is defined in the interface. Slope has also normal distribution, which is around the population parameter slope pop, which corresponds to θ2, and the variability between individuals is explained by random effect here. So now let's look how to do it in Monolix. So first, I choose a structural model from here. So I browse the model. Okay, so let's just look how it looks, how it's written in MLX-Tran language. So in the longitudinal block, we have an input. There is intercept and slope parameters, and concentration that with this definition is used as regressor. Then we have the equation and the output. So now let's go to the statistical model and task tab. And the statistical model here is separated in two. So we have observation model. As recommended by the white paper, we choose the combined one model, which is by default in Monolix, to constant model. And now in the individual model section, I define the statistical model for intercept and for slope. So for intercept, I select normal distribution. I remove, by clicking here, random effects, and I add a covariate baseline, center baseline to this parameter by selecting this box. Then for slope, I select normal distribution. We said that it contains random effects and there are no covariates. Now I can select all tasks to perform. I will save the project. And I can run all of the tasks together because it's very fast. So here we see the progress of SAWM algorithm and of remaining tasks. Okay, so the convergence indicator is okay. And let's first look at the results. In the population parameter section, we have the table with parameters and standard errors. So intercept, parameter, and slope are estimated with not very high standard errors. Moreover, in the test, we have a result of the VALS test that confirms that indeed beta parameters, so the parameter that describes the effect of baseline on the intercept, is different than 0, as the p-value is very low. Then let's look at the plots. Here in the individual fits, the plots are not smooth curves because we use concentration as regressor, and in Monolix it is not interpolated, so we have just pointwise values. Let's look at the observation versus prediction. We can see at the log scale that the points are symmetrically distributed around the y equals x line, so there is no misspecification. We can also look at the distribution of residuals. They follow the normal distribution around 0. Now we could also look at the VPC plot, not generated by default, but I can run it from here. We can see some discrepancies here. However, the general trend is well captured by the model.
All the diagnostic plots that I showed you in Monolix, they are also generated by the R package. So with so we have here the observation versus prediction. We have residuals to check if they are normally distributed. We have also residuals with respect to baseline, time, and concentration, and the quantile plot, VPC, and the plot that is time-matched plot between double delta QTc and concentration with the model prediction. And here we can see that the model prediction follows well the observed double delta QTc, which is marked here with mean and standard deviation error bars. So now, after building a model and diagnosing that it's predicting well the observations, from the white paper, we have this model, and now averaging to calculate the estimated mean, we average it over all the individuals. So the variability due to the baseline covariate and the random effects cancels out. So we have this equation that we've already seen with θ1 and θ2 parameters. However, during the implementation in Monolix, we estimated these parameters, intercept for each individual and slope, and they are defined with this intercept pop and beta intercept and slope pop and eta slope. But now if we compare these two equations, we see that this estimated mean can be calculated using directly parameters estimated in Monolix that can be read from directly from interface, from the population parameter section, or they are in the results folder that is created when you save a project. To calculate confidence interval, we could use the formulas that were given in the white paper. However, they are not general because they are not valid for nonlinear models. This is why in the R package, calculate confidence interval for simulations. So the intercept and slope are sampled from the normal distributions, which standard deviation is from standard errors that are estimated in Monolix that I showed you in the interface. So this confidence interval is this blue shaded region around the line that is the prediction of the model for the intercept pop and slope pop. In case of Dofetilide, we can see that the confidence interval at the highest relevant exposure, so here we have Cmax for a single 500 milligrams dose, it's much above 10 milliseconds that is here. This workflow is possible to do if we can compute double delta QTc for each individual at each time point. So in case of, for example, crossover studies. However, this is not always the case. And sometimes the dependent variable is delta QTc, so only change from baseline. Let me show you now how to implement this model from the white paper in Monolix. It requires additional information in the dataset because the model contains not only effect of the baseline as previously, but also effect of treatment and effect of time that is associated with the circadian rhythm. This covariates, so treatment, baseline, and time, now they are not constant in time for each individual, but they change. For example, treatment is different if we have a drug arm or placebo, the same for baseline, and time is different at each measurement time point. To use such time varying covariates, we have to split them in different occasions. So in periods where they are actually constant. And this allows to have individuals which have individual parameters that differ in different circumstances. And to do it, we need additional columns that define these occasions. Here we have additional column that distinguish between period of a placebo and period for a drug. The second column is the occasion for time, that we have for each time point of measurement, we have a different occasion. This data set is also generated with the R package, with this special columns for occasions. We have also columns for categorical cover rates. The observation is delta QTc, and also the baseline is automatically centered at the population mean. Now, with this information, we want to translate the model from the white paper to Monolix. So we have, as previously, the terms with here theta 0, which is the effect in the absence of treatment, plus the effect of 3 covariates, so of 2 categorical covariates, which is treatment and time, and the baseline. There is a eta parameter which associated with random effects on parameter theta 0, and as previously we have concentration as regressor with theta 2 and eta 2. In the structural model in Monolix, this model will contain 3 parameters, 3 individual parameters. So we have intercept, we have eta intercept, and slope. The random effects for the intercept is defined separately, and this is due to technical reasons that I will explain you in detail in the interface. So now we need to define the statistical model for each of these parameters. So let's look first at the intercept. We have, as before, normal distribution around the intercept point value. But now the effect of covariates differs from occasion to occasion. Let's, for example, look at the treatment. This term is added only if the treatment covariates equals to drug. And similarly, this term, for example, is added only if time category is equal to 1. Square brackets are indicator functions, which are 1 if the value in the bracket is true and 0 if it's false. The eta intercept is a random effect for the intercept, and we want it to be normal distribution around 0. So in the interface, we will have to set its fixed effect to 0. And the slope, as previously, is a normal distribution around slope pop, which corresponds to theta 2, and with random effects eta slope. So now let's look how to implement it in the Monolix. I will open the Monolix and load a specially prepared data set. So I start new project, browse new file, and here I have to tag these 2 columns, which are 2 occasions for treatment for the different periods, so drug or placebo, and for time. The regressor is automatically tagged, and I just have to tag covariates, so baseline as continuous covariate, treatment as categorical covariate, and time as another categorical covariate. And I can accept the dataset. Okay, now let's select the model. Okay, so here the only difference is that now we have additional parameter eta intercept. Okay, so now let's go to the statistical model. As before, I will change the error model to constant, and now we have individual model. Let me just put it like this. Okay, so here we have different levels of variability. So we have individual level, which is the same as before. But here we have additional two levels, one which is connected with the period and one with the time occasions. I said that the intercept has normal distribution and it has effect of covariates. However, you can observe that these covariates now, they are great, so I cannot add them. And this is the technical reason why the random effects for intercept are defined as a separate parameter. I can add covariates only if random effects are added at each variability level or at none. So if I remove the random effects at the individual level, now the adding covariates is possible here. So I will add the baseline covariate, and also I want to add a treatment. However, if I add directly this covariate and look at the formula, we can see that the effect will be added if my treatment equals placebo, and I want to add this effect if my treatment is a drug. So I will remove this one and I will define new covariate. So I will transform the treatment such a way that placebo now is the reference group. I accept. And now I add treatment, so we can see here that now this term is added if my transformed treatment covariate is equal to drug. And finally, I will add the time covariate to the model, which adds 16 different terms, each one that corresponds to each time category. And it means that we will have all these beta parameters to estimate. Okay, now for the slope, I change also the distribution to normal. There are random effects and no covariates, and eta intercept is also with normal distribution, but I have to set the fixed effect of this parameter to 0. So I go back to initial estimates, and it can be done here with the settings. I just fix the value and set this value to 0. So with self-defined model, I can run the task, so I can run the estimation of the parameters. However, this process is longer than previously because we have much more parameters, but I have already run it. So let me show you the results. In the individual fits are split for each occasion. So I have actually 1 point per plot because they correspond to different time occasions. But I can remove the time splitting, and here we have only 2 occasions. So we have placebo and drug treatment. We can also look at the VPC plot. Okay, and what we can do here, because we have 2 different treatments, so we have drug and placebo, I can split this plot for these 2 groups and compare the results. So also we have the values, the prediction has some misspecification, but overall trend is good. Also in the results, in the population parameters, we can see the full list of parameters, so all the beta parameters for each occasion. The double delta QTc is the difference between drug and placebo, and actually the estimated mean can be calculated with the same equation using the parameter θ1 and θ2. But now, because of the way we implemented our model in Monolix, the θ1 parameter is not intercept top as before, but it is the beta parameter that is connected with the treatment. So this is θ1 parameter. And this also can be read directly from the Monolix interface and used in the calculation of the double delta QTc at concentrations of interest, and then in the calculation of the confidence interval, as I already showed you. These two models are recommended by the white paper. However, with Monolix, we can very easily go a little further to use c-QT analysis to model directly PK and double delta QTc. And to do it, the data set will contain additionally the dose, because this is necessary for the PK part, and the observations now will contain both concentration for the drug and the values of the double delta QTcF. Let's look at this data set in DataExplore. Okay, so I start new project. Okay, so just one column left to be tagged. We can now see not only the spaghetti plots for the concentration and for double delta QTc, but also I can look at the plots of PD versus or QT versus concentration. And if we look at different individuals for this plot, we can see that there, for some individuals, there might be an effect of delay between the exposure and response. So maybe the direct model is not the best one. So let's explore it. A good practice is to first build a PK model and then add the PD part. In this case, I already explored the PK part, and here I started with one compartment model without any delay, and then improve it by adding TLAC, which decreased significantly the big criteria, exploring different possibilities. The final model, which is here noted with 3 stars, is one compartment with TLAC combined to error model and effect of transformed weight covariate on clearance. So I can open this model directly from here in Monolix. So let me do it. This is the modeling of only PK part of my data set, so of the Y concentration. I can now, to add PD part, I will go to initial estimates, use last estimates, so all the parameters estimated as my for my parameters, and I will fix these values. And now I can change my my structural model to add the PD part. So I already prepared the model for that. So I have here a model with a direct effect between PK and PD. And I have to precise as before the statistical model. So I will select the distribution. I will change the distribution to normal, remove random effects from the intercept, and add covariate baseline, center baseline as a covariate on the intercept. And now here I could already run the model, because it also takes a bit more time. I have it here already run. So let's look now at the individual fits for double delta QTc. Now the curves are smooth because we have prediction for concentration. We could also try a model with effect compartment. If I add the effect compartment, the B criteria decreases significantly. And in the VPC plot, we also can see a difference and the improvement with the prediction. There is less discrepancy between the empirical M percentiles and prediction intervals. With Sycamore, we can also compare different models. So here I compared the model from the white paper and joint model for PK-QTc with direct effect between PK and QT with effect compartment. So here we see this difference in the B criteria. When we use this joint approach, the standard errors decrease with respect to the model for the white paper. However, the values for the slope, which is the most important part, are comparable between the cases. The c-QT analysis has been approved as an alternative analysis for risk assessment if a drug has potential effect on the prolongation of QT interval. The technical details are proposed in the white paper by Christian Garnett, and contains recommendations for the design of the study that uses c-QTc analysis, and also for the models, so the predefined, pre-specified models with the list of different plots and set of results that are required for the submission. We also saw that Monolix is very flexible and is able to use both of these models and to estimate the parameters. And with the R package that we are building, the whole process can be automatic with giving just a data set and then producing the final report. Thank you for listening.